The universe is a big place. And if we're going to talk about astrophysics, we first got to start to talk a little bit about how big it is, just so we can get it into our heads. We're going to fail, but at least we can try, okay? So rather than giving you huge numbers, like millions of light years and whatever, let's scale the whole universe down, maybe by a factor of 10 billion. Shrink everything, so now in our scale model of the universe, the Earth is a 16th of an inch, little cake decoration, okay? And you can peer in there, and there's North America if you have a magnifying glass. Okay, so we shrunk the whole universe by a factor of 10 billion, and then try and see, okay, how big is everything else in this new scaled universe? Well, the sun would be kind of like the size of a really large grapefruit, and it's 50 feet away, right? And there's 9 planets. The furthest one out is Neptune, because Pluto got demoted. And it's, a couple hundred feet away, all right? And that's the solar system. There's the 9 planets, of course, and you've got one of the asteroid belt, which is like a pinch of powder that you scattered out back there somewhere. All right, it's almost nothing, right? And that's the solar system. Of course, the sun is not the only star in the sky. There's a lot of other ones. The nearest star to the sun in our scale universe, just think for a minute, how far away would that be? The sun in our scale universe is a grapefruit, so where do you think the nearest star would be? It's on the Alaska-Yukon border. And in between here and there is Saskatchewan. I mean, nothing. Anyone from Saskatchewan? I love Saskatchewan. It's a great place. Nothing like a clear, cold 40 below day with the blue sky for doing observing. Okay, and that's the nearest star, Alpha Centauri. Now, of course, it's not just the sun and the nearest star. There's actually about a cloud of 100 billion stars that forms the Milky Way. Hopefully you've been outside at night and seen the Milky Way. Now this is a ridiculously cool picture that some amateur astronomer named Axel, he traveled the world taking pictures of the sky back in the 90s and made this mosaic. I can't believe it. Anyway, it's really cool. You've seen the Milky Way galaxy, I hope, at night outside the city. Please say you have. This glow is individual stars. It's a cloud of 100 billion stars. 100 billion stars, I can't imagine how many that is, except that everybody gets 10. And the black stuff is not missing stars. That's dust blocking stars behind it. I mean, and by dust, I mean, dust. Okay, how big is this thing in our scale universe? So we've got the sun here, we've got the nearest star in the Alaska-Yukon border, we've got a cloud of 100 billion stars. This cloud in the scale universe is 63 million miles across. Dang. I can't imagine 63 million miles. So, okay, we lost. And that's just, we're trying to imagine how big the universe is, right? And we're now stuck. It's bigger than we can imagine, even when we scale it down by 10 billion, so the Earth is a little cake decoration. Okay, cloud of 100 billion stars. It's the nearest galaxy. It's our galaxy, rather. We're inside of it. This is what it would look like if we were not inside of it, roughly speaking. This is the Andromeda Galaxy, the nearest spiral galaxy to our galaxy. Once again, in our scale universe, it's 63 million miles across. In the real universe, we would say that it's around 50,000 light years across. Now, what's a light year? Well, light year is how far light travels in a year. It's kind of like running on the interstate. Like, well, how far away is Minneapolis? Oh, about 7 hours, okay? That's car hours. If you live in Chicago, it's 7 hours, right? Okay. If you live in Toronto, it's a lot more. Okay, all right, so that's the nearest galaxy. And it's not the only galaxy in the universe, of course. There's a really cool thing we can do. We can look back in time. Now, how does this work? Let's imagine one of these many, many distant galaxies here. It's 1 billion light years away. Well, it takes light 1 billion years to get here from there. So let's imagine a star explodes in this distant galaxy. That's called a supernova. Boom. Meanwhile, telescope on Earth looking at galaxy, it sees no explosion because the light is there. So we wait, 300 million years. Explosion's over. We don't see it. So we wait 300 more million. Still no there. And finally, 1 billion years later, we see the explosion. We see the explosion 1 billion years after it happens. In other words, the farther away we look, the farther back in time we look, because light takes time to travel. So what this lets us do is explore the history of the universe by looking further and further and further away. Awesome. Now, I don't know what was happening here in the past. Well, I can see what was happening about 10 billionths of a second ago, because I see you 10 billionths of a second ago. But okay, but not really that useful. And I don't know what's happening in this galaxy now. I just know what happened in it a billion years ago. But you get the idea. The farther away you look, the farther back in time you look. Okay, so I wish I took this picture. I didn't. It's the coolest picture ever taken. I just decided that. It's not necessarily, but it's really cool. Okay, this is a picture taken by the Hubble Space Telescope. Hubble Space Telescope is a telescope, imagine a 2.5-meter diameter lens. And the camera has not a 60-second exposure, but a week exposure. And how big a sky is this? Okay, take an American penny. You're allowed to do this. You can't do this in Canada because it's illegal. And also, we got rid of the penny. Take the penny, drill a hole through the eye of the president, hold it up, and look through the hole through the eye of the president. There we go. That's how big this amount of sky is. So it's a tiny little spot of sky. They chose a place in the sky that had no stars in the foreground. Everything you see here is a galaxy. Remember what a galaxy is? It's one of these clouds of 100 billion stars. That's like 50,000 light years across. Okay, so you can tell, I mean, that looks like a galaxy, and let's look at those three up there. Those look like galaxies, right? Kind of a spiral thingy, and these guys here. But it turns out that absolutely everything in this picture is a galaxy. That's a cloud of 100 billion stars. That's completely ridiculous. But really cool. All right, now, it takes light to travel to us from here. The typical distance to these galaxies is something like 7 billion light years away. So we're seeing the universe, some of them are closer, some of them are farther, but kind of on average, kind of like it was 7 billion years ago. Now, that's pretty cool. We notice something really interesting when you look at these galaxies. This was discovered back in the 20s. Every one of these galaxies is moving away from us. And the further they are from us, the faster they're moving. And that's true for galaxies in that direction, and it's true for galaxies in that direction. No matter which direction you look, galaxies are moving away from us. And the further they are away, the faster they're moving. Would you want to try and imagine that you're at the center of the universe and everything's moving away from you? So have you ever wondered, it's like, I feel like I'm at the center of the universe. Yes, you are. Now, it turns out, by the magic of something or other, magic of arithmetic, that if you're sitting on this galaxy and you look at us, well, you say, oh, that galaxy is moving away from us. So it doesn't matter where you are, everything's moving away from you, right? If I'm moving away from you, you're moving away from me. How do I know where 0 is? So the whole universe is expanding, and it all looks like it's moving away from whoever you are at the center. Whole universe is expanding. You're looking further and further away, looking further and further back in time to when the universe was, when everything was closer together in the past, right? If the universe is expanding, then in past things were closer together. So if you look at some of these galaxies, you'll see a lot of them are undergoing interactions. They're colliding and otherwise having troubles, which aren't happening now because the universe is expanding and things are getting further apart. The further away you look, the further back in time you look. The further back in time you look, the closer things were together. Make sense? This is about design, right? Okay, so as the universe expands, it cools. Right? You could take a gas and let it expand. What happens? It cools. That's how a refrigerator works, right? There's a compressor that compresses the gas, it gets hot, blow the heat out the bottom, then goes into the fridge and expands and cools. Okay, so when the universe is expanding, it's cooling. So the further away you look, the further back in time you look to when things were denser and denser and hotter. Okay, well, let's take this to the silly limit, because that's what you need to do when you're a physicist. What happens when you go far enough away so it's really dense and really hot? Well, what does really hot, really dense gas look like? Well, the sun is really hot, really dense gas. It's plasma. So in principle, I should be able to go outside at night, look at the sky in any direction, and behind whatever's in front, look far enough away to look far enough back in time to when the whole universe was a hot, dense, glowing plasma. Kind of a picture like this. So here we are in the center of the universe, and there's all these galaxies moving away from us, and we look further and further away, we look further and further back in time to when the whole universe is filled with this hot, glowing plasma. And of course, you look a little further than that, you go past the beginning of the universe, and that's where dragons are. Okay. How many of you have gone outside at night and looked at the sky and seeing it glowing like the surface of the sun? Good. Excellent. Okay, so what am I missing in the story here? Right, last thing, remember? The further away you look, the faster things are moving, right? So this plasma is moving away from us ridiculously quickly, almost at the speed of light. Now, you've heard a train go by, right? Or a fire engine, okay? So in Surrey, in BC, when I grew up, they painted the fire engines green, and I could never figure that out. But my theory is that so if they're driving away from you, at about half the speed of light. Instead of looking green, they look red. Okay, what am I saying here? If the source of a wave is going away from you, the frequency goes down. So the sound from the fire engine, when it's going away from you, the pitch is lower. When the light coming from the fire engine is going away from you, it shifts to a longer wavelength. Instead of being green light, it becomes red light. It's got to be going half the speed of light, so I've never actually seen that, but we can be fanciful. This plasma is going away really fast. So instead of being visible light that I could see, the whole sky glowing like the sun, it ends up being microwave light. So it turns out that if you build a telescope that can see microwave light and look at the sky, you do in fact see this glowing plasma in any direction you look, and I'll be talking about that shortly. So here we are. That's the universe. Now, turns out, a little bit of physics, anything that's warm glows. From millions of degrees is X-rays, tens of thousands of degrees is UV light. This is above absolute zero, so this is degrees Kelvin above absolute zero. Thousands of degrees, visible light, so 3,000 degrees, your light bulb filament glows, you can see it. Hundreds of degrees, infrared light, the heater on your stove, you turn it on, it's not glowing red yet, but your hand can sense it. It's sensing infrared light, that's hundreds of degrees. Tens of degrees, it gives off a radiation called submillimeter light, which you've probably never heard of because it's not very useful. And then a few degrees would be microwaves. So if you want to look at things that are these various temperatures, you need to build telescopes that can sense those wavelengths of light. So normally we think of telescopes as viewing just visible light. That only can see things that are thousands of degrees. What if we want to see interstellar dust? Remember that black stuff I showed you in the picture of the galaxy? That dust is sitting at a few tens of degrees above absolute zero. If I want to look at that, I need to build a submillimeter telescope. That plasma that I talked about at the beginning of the universe, that's been redshifted until it acts like it's about 3 degrees Kelvin. I'm going to need to build a microwave telescope. So I need to build submillimeter and microwave telescopes if we want to explore those parts of the universe. Well, you can do that, and there's awesome groups at Caltech and JPL where I collaborate that can make these amazing detectors. But there's an issue, and that is the atmosphere, air, is not transparent to submillimeter light. So I can go out at night and look at the sky in visible light and see right through the air. If I take my submillimeter telescope and point it at the sky, I see the air in front of me. So we're kind of stuck. That's one of the big reasons why nobody uses submillimeter light for anything, because it can't travel very far. Okay, so the obvious solution is to put it in space. So here's the Herschel Space Observatory. It's fantastic. It works great. It cost $1 billion. Turns out they don't let graduate students play with billion-dollar telescopes. And so what we do instead is this. We fly our telescopes on stratospheric balloons. They're big, so 1 to 2 million cubic meters. They can go 40 kilometers high, so 130,000 feet. So 4 times higher than a jetliner. 3,000 kilogram payloads, so that's 8,000 pounds in American. They can have flights up to 50 days long, or in American about 50 days. So here's a picture of one of our telescopes in Antarctica getting ready to launch. Oh, why Antarctica? You've taken a party balloon outside and let it go, and they say, oh, it's just going to pop, right? Because it goes up, and as it goes up, the gas expands, and it pops and falls, right? So when we take our balloons, ready to launch here, it's only about 0.5% full. The idea is we're going to launch it, and as it goes up, it fills and fills and fills until when it's at 140,000 feet or 130,000 feet, it's full. And then it goes a little bit higher and pops. No. It's got a vent at the bottom. So when it's completely full, a little bit of gas vents out the bottom, and then it just floats along. So if you launched at dusk, say from New Mexico or something where it's a nice place to launch, you can't land on people, that's great, goes up, floats along all night, sun rises, shines in the balloon, gas in the balloon warms up. Gas in the balloon warms up and expands, the balloon pops. No, it vents out the bottom, you float along all day, life is good. Sun sets, gas cools, balloon is not full anymore, and down you come. So if you launch from mid-latitudes, you get a day's flight. But we don't want a day's flight, we want weeks' flights. So we need to get rid of sunsets. Hence Antarctica, where the sun just goes in a circle. Okay, so, and of course what this really is just a killer robot on a balloon. So off to Antarctica, we get to fly down in luxury accommodation, the C-17s here. They actually have seats. We used to have to fly down in C-141s, don't recommend it, especially since they've retired them all. Yes. Land on the ice. This is McMurdo Sound. This is the furthest south that the ice melts in the heat of summer, when it gets up to 0 degrees. But when we land, it's still about 15 feet thick of ice. So they can land the C-17 on the sea ice. In about a month, this will just be slush and water. We live in the town of McMurdo, which is sort of an academic's paradise because you live in a dorm and eat in a cafeteria and there's no money for 500 miles. About 15 kilometers outside of town is our launch facility. We actually work in this building here. Turns out this building is the largest building in the world on skis. I mean, there had to be one, and that's it. So here we are starting to put together our telescope, and it sort of looks like a welded aluminum frame because it's a welded aluminum frame. And we bolt all of our electronics and everything to it. This is a great place to work. Comes equipped with heated floors and graduate students and everything you ever could want. So we go down there for a couple of months getting the thing put together. Finally, it's ready to go. Here's the telescope fully assembled. It sort of made a transformation in appearance. You can see here the primary mirror for the telescope. It's a 2-meter mirror. The secondary. And then it's all covered in aluminized mylar. And that isn't just to make it look nice. It's to keep the sun off the optics. We're looking at very cold things, and we don't want to warm up our telescope. Here it is in the launch vehicle, getting ready to launch. Solar power. Can't run an extension cord to 140,000 feet, but fortunately the sun's up all the time. So we power it through solar power, getting ready to launch from the launch vehicle. So let's go through a launch sequence. This is the balloon, fully inflated and ready to launch. The balloon actually extends all the way over to about here somewhere. It's only about 0.5% full, because it's going to expand by 200 on the way up. And what he's going to do here is this spool is about to pop open, like so. And that releases the balloon. It gets up, and when it's just about right overhead, these guys' job is to drive the launch vehicle right underneath the balloon, and then release it, and away goes the telescope. So you can see the balloon starts up here. It's hanging from the parachute, and then a flight train, and the telescope pointing here, hanging there, and away it goes. Bye-bye, blast. And then we spend the next 2 weeks staring at computer screens and occasionally panicking because something breaks and then you have to fix it. That was our path for this particular flight. In general, you launch from here, McMurdo, and the balloon blows around somehow or another. One year we had it come right back and landed within sight of the base. That was great. This particular flight that I'm showing you here was less successful. I came down in the parachute, it landed, the parachute didn't come off, there was 20-knot winds, it dragged 135 kilometers across Antarctica and ended up in a crevasse where it remains, never to be seen again by man or beast until the end of all things. But we got the data back because the hard disks fell off. One of the things we saw here, these are all star-forming galaxies. One of the big questions we had was, where do all the stars come from? When we looked at the Hubble images, you see all these galaxies, but not near enough star formation in order to create the number of stars we see. Turns out stars are being formed hidden inside these dusty clouds. We're able to calculate all these dusty galaxies, find the amount of star formation from them, and now we understand where all the stars come from. The universe come from. They come from these distant galaxies. That's cool. Another thing we did, here's our galaxy. We looked in this region here. You can see the dark stuff blocking the starlight. You can sort of see that here. That's the image we got in the submillimeter. So this is actually looking at this dust glowing. Now, this is actually 3 colors in the submillimeter, and I've kind of pretended they're visible light using GIMP, just so you can get the idea. Blue stuff is warmed up by recent and current star formation, and the orange stuff is where there's not really any star formation happening yet. Zooming in here, you can see these little nodules, which are about to become stars. So it's pretty cool. Understand star formation, that's not bad. What else have we done? Way a long time ago, when I was but a wee lad, we built this thing called Boomerang. This was back in the days when digital cameras were 800 by 600, hence the high quality picture. This is the picture we took of that primordial plasma. Remember, we're looking really, really distant. This is the universe as it was 300,000 years after the Big Bang, or 13.7 billion years ago. And what was it like? Well, pretty uniform. This is a massive color stretch. Done a color stretch by a factor of 100,000 to see anything. If you just did it naturally, it'd just be completely uniform. What do we conclude? Well, geometry of the universe. It's Euclidean, flat. This is a huge question, right? And which you don't care about, but it's really interesting. Age of the universe. Well, it's 13.7 billion years old. That is to say, not infinity and not 0. Well, I knew it wasn't 0. Well, I suspected it wasn't 0. We discovered that the content of the universe was 5% normal matter, stars, dust, cheeseburgers. About 25 or 30% dark matter. Well, some of it's neutrinos, but most of it's Star Trek particles. When Geordi says, oh, there's an axion beam. It's those things. Particles. We don't know what they are yet. We're looking for them. The people are looking for them at the big super collider and things like that, and down in deep mines. We'll probably find them. And then the rest of it is dark energy. And by dark energy, I mean, I don't know. Nobody knows. We don't have a theory for what it is. It's the stuff that makes the expansion of the universe accelerate. It's a huge mystery what it is. In fact, people don't even really know how to address it. So what do we do with this? This universe we've come to understand. We can really now track out the history of the universe pretty much from, close to the Big Bang to the present. We know when stars are being formed. We know when galaxies are being formed. We know how the universe is expanding. But we discovered that the universe we've got is kind of odd. Like, not the kind of thing you'd expect if you rolled the dice, or if you rolled the dice a billion times, or a billion times, or a billion times, or, okay, so it's kind of like fine-tuning on the order of a part in 10 to the 40th on a good day. It's kind of like less likely than you would expect a human brain just to form in space that thinks it saw the universe. So we got some serious unknowns, right? We understand a lot about what's happening in the universe, but in terms of how it could come to be like the way it is, which is kind of a design problem, remains really unknown. So one of the things we're going to try and do is probe right back even closer to the Big Bang. It turns out that theorists tell me that maybe, if the theory is right, or if a particular theory is right, there might have been gravitational waves emitted in very, very close to the Big Bang, 0.30 second after the Big Bang. We expect maybe there were gravitational waves emitted. So we've been building this experiment called SPIDER, which is designed to go look after that. So looking right at the very beginning of the universe. And we're going to try and fly that this Christmas. So it's actually on a ship down to Antarctica right now, and we'll be heading down shortly. So history of the universe, SPIDER is looking at this point, Boomerang looked at that, and this is sort of the story. So I could talk for another 2 hours, but I'm out of slides, so I'll leave it there.